For our next talk, we're going to have Eirik Larsen talk about EarthNET and beyond, harnessing big geoscience data for mining and what we can learn from the energy industry.
Thank you. So I'm from Geoscience Analytics, now IMDEX. And Geoscience Analytics is a company that I founded together with two other guys 10 years ago in May this year. So we've been around for a while, and we have been working in the oil and gas industry. So if you hear some language that is a bit alien to the mining community, that explains it. And now we are in IMDEX, and we're integrating, started to integrate our products from oil and gas into the mining industry to collaborate with the rest of the IMDEX family and the whole portfolio of products available there. So just to start, just a little bit on the background of why we started the company. So the three of us, I'm a geologist, one of us is a geophysicist, and the third guy is a physicist, but also a data scientist. And we had geoscience, applied geoscience positions in the industry. We also had managerial positions. I was, for some years, exploration manager for a company. So we really learned how important it is to use data right in order to make good decisions. So we are responsible for informing the investors properly so that they invest their money wisely. So we set out to basically solve a few problems. So I highlighted today four of those. So the first one is basically data discovery. So when we work in exploration in particular, there's a lot of legacy data that is available, but a lot of the time we struggle to find it. And a lot of the time of geoscientists are basically spent searching for data even before we can start working. Once we find it, of course, we have another problem. That's data curation, data cleaning. There was mentioned earlier here that good data in is important to have good data out, of course. So that's a huge challenge to solve that. And then number three, as was talked about by Ryan, interpretation efficiency. There's a lot of tasks in geoscience that are easy to automate with AI solutions. And we can solve these geoscience problems in isolation. So we can work with core images in isolation. We can work with sensor data, downhole geophysical tools in isolation. But we want to integrate these data types. So that's the fourth problem, the data integration problem. We kind of need to solve all of these in order to have a system that efficiently supports this data-driven decision-making that we all want to achieve. So in order to achieve these ambitions, we set out to build EarthNET. That's our product. And EarthNET is many things, as you can see from this overview. So at the base of EarthNET, we have the so-called EarthNET data lake, which is basically a data platform. It can host all kinds of geoscience data from samples from the lab, XRF, XRD, and all these things, all the imagery from the microscopes and the core imagery, the CHIPS imagery, the petrophysical data from the downhole sensors. And in oil and gas, we also use a lot of seismic data, so also that. And the structural interpretation. So all of this data lives in a data platform. And that's a deliberate choice to separate that data platform from the applications that are on the layer above. And that is because we want to achieve integration between data types and disciplines via this data layer, and not necessarily only directly through from one application to the other. This addresses a problem that has been very prevalent in oil and gas. It's the so-called data silo problem. So every application has its own data storage, and that makes it difficult to achieve this integration between the disciplines and the data types. So integration through the data layer is what we have gone for. And then on top of all of this, we have the layer to retrieve the insights from the data that was interpreted in this suite of applications. So to dive a bit deeper on each of these problems. So the data discovery problem. I didn't find the value of X. There were so many quotes out there. So Geoscience spent X amount of their time looking for data. And I've seen quotes as high as 50%. But the point is basically it's a lot of time and it's unnecessary. So let's just make sure we find solutions to basically bring all the data to the fingertips of those who need it. And basically pull it out of these silos. We have so much data, and because we don't find a lot of it, because it takes so much time to interpret each individual data type manually in the traditional ways, we typically end up using only a fraction of the data to support the decisions. So enabling the use of all relevant data is one way to better inform decisions, getting rid of these data silos. And this is what we have tried to achieve with this EarthNET data lake. So it is we liberate it from the silos, meaning that we can connect the system to any data storages that already exist. So a lot of data does not really need to be ingested into the system. We just link it to the storage where it already is. So to minimize duplication wherever possible. We built a multi-user collaborative environment. So many users can work on the same data at the same time, collaborate on the projects. We want very fast access to data, especially this high volume data like seismic. These are multiple terabytes per file sometimes. So in order to query this, sometimes we do need to duplicate in order to get the data into modern formats and not only work with formats that were originally designed to be read from tapes. And we want this curated analytics ready data so that we can integrate with the different data types. And the system also connects to third-party systems, to OSDU, which I've heard is also making some groundway in mining industry. So data harmonization is something we didn't understand the magnitude of this problem when we started, but this is basically where we have spent a lot of time. So data cleaning is one thing, flagging erroneous data. There is a lot of erroneous data in oil and gas. People have recorded data in feet instead of meters and vice versa. There are negative densities out there. There's all sorts of things that are easy to write code that discovers these kind of ridiculous mistakes, and so we can flag them out. And sometimes we can find solutions to replace the wrong data with the correct data, or in other instances we just have to flag it so that we don't feed it into the workflows. So this is what we call data cleaning and harmonization. And we make sure that in these processes, we add metadata to whatever is produced so that it is traceable. So we can, if something happens to propagate downstream in the workflow and a mistake is discovered downstream, you can trace it back to the source, make a correction, and run it again. And next time, it will not make the same mistake again. So we have also the data formats. There are so many different data formats in oil and gas to deal with, both for the lab data, the sensor data, the seismic data. So we built a system to be agnostic to all formats that we have worked with so far. We'll continue doing that as we encounter new formats in the mining industry. We don't want to underestimate the importance of data review and QC, as was mentioned earlier. The plots at the bottom, middle bottom, illustrates some outliers to the left where some wrong units were used. We can discover that, correct it, and use better input. In the block to the right, you also see that there are data gaps. This is from downhole geophysical sensor data. Machine learning methods is also very good to fill such gaps. If you have some of your tools that were behaving well and some that didn't, or simply in some sections, some measurements were simply not recorded, it is in many cases possible to predict one property as a function of the ones that were actually measured. And by doing so, we can increase the abundance of data as illustrated here, from very little lithology data initially to thousands of meters, and very little sensor data also to thousands of meters of sensor data. And all this is done by machine learning models that are, of course, tested and QC'd and blind tested and scored. And all these outputs comes with confidence metrics and also uncertainty quantifications. And then there's the data interpretation efficiency problem. So this is what we looked at in the interpretation of imagery, core, chips, cuttings, as we call it in oil and gas. And this is where a lot of the geoscientists spend most of their time, just doing manual repetitive work. In oil and gas, interpretation of seismic is the big time drain. And these repetitive tasks are kind of perfect to automate with machine learning, because we can teach the models to behave like the humans do when they interpret the data, and speed it up from months to days, basically. We do certainly want to keep the human in the loop. Somebody has to be accountable, responsible. You don't want to still until maybe someday in the future you want to have a check that these AI models are doing the right thing. So the software is built very much to have the human in the loop and to basically facilitate that AI-assisted geoscientist that James talked about. And here's just one example from oil and gas. All the colorful data here are machine learning interpretations. So to the left, these are interpretations of downhole sensor data. So we have a lithology column, we have a porosity column, and we have a water saturation column. And these are key to understand where we have the reservoir, where the reservoir is porous, and where it is filled with oil or gas. And from this, we can predict where we have these so-called pay zones. We can classify them according to quality and thickness and so on. And the point with this example here is that you see the thick yellow unit at the bottom that has this green marking to the right. That was a known accumulation of oil. But the machine learning model also found some thin streaks of green above there where it says predicted pay. So those are very thin. Initially, you can ask yourself, is it just noise? Is it some error? But it has passed through the error, the kind of the filters and this process, QC process. So then you can think of this as a smoking gun. It's too thin to be economical on its own in this particular location, but it's maybe a smoking gun that something is happening on the side. So that's when we bring in the seismic data, it's three-dimensional regional data, and we use another set of machine learning models to be able to predict the lateral extent of this accumulation. So on that image to the right, the little green blob at the bottom above the building label there was the originally known accumulation. And following this process, we discovered the much larger one to the right across that fault. And the faults here are also interpreted by machine learning models. So that also illustrates a bit of integration. So we integrate interpretation of these downhole geophysical logs and the seismic data. And we achieve this by utilizing this setup with a data platform and the individual applications that deal with the specific data types. But we can also integrate with the lab data, the sample data, as is shown in this example here. So to the left, we have the interpretation of the chips or cuttings. This is also done with both classification, object detection, semantic segmentation. These models kind of QC each other. So if you have agreement between them, it's better than if you have disagreement and so on. And so they all come with different scores, confidence scores. We then move the interpretation of those, which sit on a sampling rate of like 3 to 10 meters, into the geophysical log space, where the sampling rate is 15 centimeters or half a foot. And that knowledge that came from the rock sample interpretation becomes the ground truth to train the petrophysical models that interpret the logs. Then we insert the borehole logs into the seismic, of course, with the highest precision, location precision that we can have, which is a challenge because logs are measured in depth, seismic is measured in time. So you need to overcome this alignment problem as well. But once they are aligned, you have these pairs that allow you to train the supervised models to then interpret the rock property directly from the seismic. Which is shown here from sample to log, and here in the final step, it goes from log to seismic. And in this particular slide, it's the percentage of the sand lithology in this vertical section that is multiple kilometers across. And all the ground truth that was injected into this workflow was the interpretation of the samples. So we propagate the information from where it is most solid in the samples itself, through the borehole geophysics, through the seismic data, and we end up with 3D geological models. So finally, when we have achieved the interpretations of each of the individual data types with the appropriate quality control data and the integration of each of these data types, we need to get to the decision support step. So that's why we built this EarthInsight application that runs on top of everything. So that allows you to ask questions to the data. And we partnered up with a company, Iraya, in KL, who built a large language model, agentic AI system. So we built APIs to connect that to EarthNET. So the end users can now write in natural language a question. So the question here is, can you compute the net pay for this particular well? And the system answers with this statistical data in the table and also the graphics in the EarthNET viewers. We can also do it without that AI agent, simply by filtering in the application itself. But for many, it's very convenient just to be able to ask in natural language. So having a system like this allows us to do projects at a really large scale. So at the scale of countries, thousands of boreholes in a matter of like a couple of person months. We can do this. We have done it for multiple governments in Norway, UK, and Malaysia. And now we are in the process of integrating with the rest of the products in the IMDEX family. So building APIs to ingest, harmonize, integrate, interpret, query data. So Mining is also data rich. We see after half a year of collaborating in IMDEX that there's a lot of similarities with oil and gas on the data side. Although the problems that we ask, the questions that we ask are different, there's a lot of similarity. And we think that this will be a very useful addition to the product suite of IMDEX going forward. So thank you very much.
Thanks very much, Eirik.